Greetings from the Department of ECE, SJBIT. In this session, you are going to learn about CO and ARM microcontroller subject, which is for 5th semester. And in that first module we'll be starting with, which is about the basic structure of computers and I/O organization. Here in this subject you have both CO and ARM microcontrollers. CO is about 2 modules, computer organization, and ARM microcontroller is about 3 modules. Coming to VTU syllabus, this is a VTU syllabus which you can go through. It consists of 2 parts. First part, which will be dealing with the basic structure of computers, and in that I will be discussing about the operational concepts, basic bus structures and the performance, addressing modes, assembly languages, basic I/O operations, stack and queue, subroutines, and all these things. And in part 2, which will be dealing with the input-output organization, that is interfacing, accessing the I/O devices and interrupts. For that, we'll be following this textbook, which is Karl Hemmercher, which is available in the library. You can go through. So coming to the first module, contents. These are contents of part A. So as I have told you, we'll be dealing with operational concepts and bus structures, performances, addressing modes, assembly language, all these things about. So first, before I start with computer, classes of computer and the functional units, all those things, as we know that in simple terms, the computer or a digital computer, which is defined as a fast electronic calculating machine that accepts digitized information and processes that according to the internally stored instructions and produces the resulting output. So as I have told you, processes the list of internally stored instructions, which we call it as a program, and as it is mentioned, internally stored, so usually it has to be stored in a memory, internal memory. So there are many types of computers that exists and which they differ in size, cost and computational power, as well as the intended to use. So commonly these are the classifications of a computer. First one, if you observe, desktop computer or laptop computer, which we will use for a general purpose, and a variety of softwares can be installed into it, and it is subjected to cost and performance trade-offs that you have, obviously. Suppose if I want a good performance, cost of that has to be increased. Then coming to the workstations, compared to desktop computers, workstations will have a more computational power, mainly used in engineering applications, graphics, and so on. Coming to the next one, which is enterprise system or mainframe computer. Mainly it is meant for business applications, data processing. And apart from that, you have a server systems, which is nothing but if you have a n number of computers which are connected to a main server, network based, which is of high capacity, performance and reliability, as well as that servers can range from small servers to a building of size. And we'll have a supercomputers also, which is of higher end range, and they are meant for large numerical calculations like weather forecasting, aircraft design, and so on. And we have embedded computers, most of the embedded systems which we were making use of, which is hidden in it, components are hidden in it, and which is stringent in power, performance and cost constraints that you have. So we have seen the definition of a computer, then followed by the classes of computer. Obviously, classification is with respect to size, cost, computational power, and the use, intended to use. Coming to the functional units in a basic computer, if you observe, basically it has 5 functionally independent main parts. So you have a input and memory, arithmetic and logic unit, output and control unit, as it is shown in this figure. So the input unit, purpose of the input unit is to accept the information, coded information from human operators, or it can be from electromechanical devices such as from keyboards, or from the other computers or digital communication lines. So the information whatever it has received, it can be stored either in memory. The information received will be stored in memory, or it can be stored in internal memory for later reference, or it can be immediately used by the arithmetic and logic circuit. So this arithmetic and logic circuit, which will perform the arithmetic and logic operations, desired operations will be performed by that. The processing steps which are determined by the program, they are stored in the memory, program intent. Otherwise we can say program will be stored in the memory. Finally the result will be sent to the output unit. All these things will be controlled by the control unit. Majorly the control unit which will control all these processes. Okay. So basically, as I have told you, arithmetic and logic unit in conjunction with the main control unit, we call it as a processor. Whereas input and output together, we call it as IO unit. Memory is an independent unit which is meant for storing the instructions or the program. So coming to the memory unit, so which is meant for storing the programs, or it can be data. There are majorly two classes of storage that you have: primary storage and secondary storage, or primary memory and secondary memory. Secondary memory, which is of larger one, but it is cheaper one. Coming to primary memory, which is fast, programs will be stored in this memory when they are executing. Large number of semiconductors were used as a memory cells or storage cells. So the data can be processed from the memory in terms of words. In order to get the data, you need to give the address of that memory. So address has to be mentioned. You have a RAM, random access memory, a read and write memory, read-only memory, two different types that you have. Secondary storage usually ROM, and primary storage usually it is RAM, or cache memory, or main memory we call it as. So we'll see in detail about this memory in the memory unit. So basically you remember, memory unit is meant for storing the programs, or it can be of data. You have two stages in that, two classes in that: primary storage and secondary storage. Now coming to the arithmetic and logic unit, ALU we call it as. It is the heart of the processor. Most of the arithmetic and logic operations will be executed in the ALU processor. It loads the operands from the memory. Operands, it could be data. Opcode is the one mnemonic, and brings them to the processor and performs the operations, ALU, logical, arithmetic and logical operations. Stores the result after performing operations. The result will be stored either back to the memory, or it can be stored in the processor itself. So you'll have a registers inbuilt within to store the result or to perform some operations. Fast control of ALU can be done. Then coming to the control unit, so all these operations which will be controlled, all the computer operations which were controlled by the control unit. The timing signals which governs the IO transfer are also been generated by the control unit. So control unit is usually a distributed thought throughout the machine instead of a standing alone. It is distributed one, means timing signals which has to be generated, as well as all the controlling actions which will be controlling signals which will be generated, all these things which will be distributed throughout the machine. Coming to the operations, as already I told you, it accepts the information in the form of programs, or it can be a data through an input unit, and stores that in the memory, fetch the information stored in the memory under a program control into the ALU, where the information is processed. So the processed output the processed information through an output unit. All the units, all these control unit which will control all the activities inside the machine through a control unit. This is what about the functional units in a computer. And the information handled by the computer is it is in the form of instructions, or it can be sometimes called as a machine instructions. What it will do is it governs the transfer of information within the computer, as well as between the computer and the other IO devices. It can be within the computer, or it can be from the computer to IO devices. So, and the instructions can be used to specify the arithmetic and logical operations to be performed. Means the instructions related to that also. And you have a list of instructions that performs a task, which we call it as a program. Coming to the datas are the numbers and encoded characters that are used as operands by the instructions. The term usually is often used to mean any digital information which is known as data. Entire program which is considered as a source, means high level language, low level language, and object program. We have different kinds which we will see further in another chapter. So the information binary digit, or we call it as a bit, which is encoded in a binary code that is in the form of zeros and ones. Information which has to be handled by the computer must be encoded in a suitable format. It is in the form of bit, which is the binary digit in the form of zeros and ones. So mainly the operations of a computer, which includes accepts the information in the form of program and data through an input unit, stores that in the memory. Information stored in the memory is fetched under the program control into an arithmetic and logic unit, where it will be processed. The processed information leaves the computer through an output unit. All these activities are controlled by or directed by the control unit. This is about the functional units of a computer. Next we will look into the basic operational concepts. So already, as we have seen about the activities which are performed in a computer, and that will be governed through an instruction. So to perform a task, an appropriate program consisting of list of instructions which will be stored in the memory. This already we have discussed. Individual instructions which are brought from the memory into the processor, and that will be executed, which executes the specified operation. It can be data, moving a data, or it can be arithmetic operation, or it can be logical operation, any of such kind. So data to be stored or data to be used as operands. So that can be stored either in memory or in registers. If it is in the memory, we need to fetch that data from the memory. Suppose if I consider some typical instruction, so which is something like add. Add is an arithmetic operation, location A, R0. So add is an operand at a memory location, which is the address of that is specified as location A, to the operand register operand in the register R0 to the processor. After performing a sum of the two contents, that means the content in the memory and the content in register, they will get added, and the result will be placed in the register R0. The original contents of location A, it will not be erased off, it will be preserved. Whereas the original contents of R0 will be overwritten. Suppose if I consider the data here as 05 and here as 06, 04, then these two will get added and the result will be stored in R0 itself. So original data, original content in R0 will be rewritten. So first what the computer will do, so it fetches the instruction from the memory and it will be placed into the processor. The operand which is available at location A is fetched, again it is in memory, and it is added with the contents of register R0. The resulting sum which is stored in register R0. Similarly, can we guess what happens with these instructions? So first instruction says that it is load, name itself indicates it is loading the content. Whereas second instruction, similar to the previous one, here you can observe add R1, R0, indicating the contents of register R1 which will get added with R0 and the result will be stored in R0. So that means the contents of R0 will be overwritten, whereas R1 it is preserved. Coming to this location, first instruction says load. First instruction says it is a load. So load the contents from location A, that is suppose in location A I have a content as 04, that will be fetched and it is stored into register R1, internal register. So whose contents will be overwritten? In these cases register R1 contents will be overwritten, whereas in this case register R0 contents will be overwritten. Understood? So coming to the next one, similarly we can say that this is a diagram which is illustrating the connections between the processor and the memory. So where you can observe you have a memory which transfers between the memory, shows the memory and the processor which are connected. It also shows a few essential operational details of the processor that have not been included in this. The interconnection pattern for these components, which is not shown here completely, which will be seen in next. So in addition to ALU, arithmetic and logic unit, and the control circuitry, we'll have in the processor a number of registers. So you'll have n general purpose registers which are meant for several different purposes. So and you have different registers, special purpose registers like instruction register IR. It holds the instruction that is currently being executed. Its output is available to the control unit. Actually that will generate the timing signals that controls the various processing elements involved in executing the instruction. Next we have is a program counter, which is PC, another specialized register. It keeps track of the execution of a program, or you can say that it contains the memory address of the next instruction to be fetched and executed. It holds the address of the next instruction to be executed. During the execution of an instruction, the contents of PC will be updated to correspond to the address of the next instruction to be fetched. Now coming to this one, n general purpose registers that you have, that is from R0 to Rn-1. All these things will be seen in next further following slides. The two registers, finally the two registers that you have, which is to facilitate the communication with the memory, they are memory address register, which we call it as MAR, and memory data register, MDR. MAR, it holds the address of the location to be accessed. Name itself indicates memory address register holds the address of the location to be accessed, whereas MDR contains the data to be written into, or it is read out of the address location. It can hold either the data to be stored or data to be read. So as we have seen about the different components which are connecting between the processor and the memory unit. You will have a arithmetic logic unit, control unit. Along with that, you will have n number of registers, MDR, MAR, some specialized register like IR, instruction register, and program counter. As I have told you, the same thing: instruction register, program counter, general purpose registers, MAR and MDR. Purpose of that, as I have told you already, I'll just revise it. Programs inside the memory through an input device, resides in the memory through an input device. PC program counter is set to the point of first instruction first. The contents of PC will be transferred to the MAR, memory address register, will read the signal which is sent to the memory. The first instruction is read out and that is loaded into MDR data. The contents of MDR, again it is transferred to instruction register IR, the one which has to be executed, and that will be decoded and executed. So basic operation units, if you conclude, get operands for the ALU. So operands means the data. It can be from general purpose registers or it can be from memory. If it is from the memory, we need to first store memory address into MAR, then read that, then that data will be stored into MDR and then to ALU. So after getting the operands, means the data, the ALU will perform the operation. After performing the operation, the result will be stored back. Either it can be into the register or it can be to memory. So if it is to the memory, you will be writing it. So if it is read from the memory, we call it as a read. If it is writing into the memory, store, load and store. So during the execution, the program counter will be incremented to the next instruction being executed. This is about a normal execution of an instruction which are stored in the memory. So how the instruction will be and how about the data that you will fetch and execute it. So apart from that, we'll have another concept called as a interrupt. Name itself indicating, so you are interrupting the device. So normal execution of the programs may be preempted if some device requires urgent service. So it will be stopped. Normal execution of the program will be stopped. Suppose if some device requires an urgent service of the current program must be interrupted. So the device, it raises an interrupt signal. So once if it raises a signal, interrupt signal, and the controller or the processor which will execute the interrupt service routine, ISR we call it as, interrupt service routine. Current system information means which program, which instruction it is executing. All these backup will be stored in some program counter, general purpose register, control information, specific information. All these things will be stored and retrieved it back after completing ISR. This is about the interrupts. So now coming to the next topic, which is about bus structures. So name itself indicates bus is nothing but how you are connecting different parts inside the computer together. So a bus is nothing but a group of lines that serves as a connecting path for several devices. We call it as a bus. You have different buses. We have a address bus, data bus and control bus. So here you can observe the structure of a bus. It can be single bus or multiple buses. This is the one indicating single bus structure, where the different components will be interconnected through different buses. Interconnection from input to output, or input to some other memory, or input to processor, or from processor to output or input. All these connections will be established through buses. So bus, as I have told you, it is nothing but a group of lines which are meant for serves as a connecting path for several devices. Coming to multiple buses, different means instead of having a single bus, you will have a multiple buses also. Means with the single bus, advantages, it is of low cost and flexibility for attaching the peripheral devices. Systems that contain multiple buses, they achieve more concurrency in operations, allowing 2 or more transfers to be carried out at the same time. It can be achieved through multiple buses, but problem means advantage with that is multiple buses is at the same time you can transfer the data between multiple devices, but problem with that is cost of the system will increase. Performance and cost trade-offs that you have with multiple buses. Coming to the speed issue, different buses have different transfer or operating speed. If the speed of the bus is bounded by the slowest device which is connected to it, the efficiency obviously will be low. So how do we solve this one? Means a common approach is by using buffers. So using a buffer registers, that is an example like a printing characters that you have with the devices to hold the information during the transfers. So coming to the next one, which is about the performance, next topic of this interest, which is of performance. So the most common or important measure of a computer is how quickly it is executing the programs. So majorly it depends upon 3 factors. One is the hardware, another one is the instruction set, and another one is a compiler. So these 3 which will decide the performance of a computer. So coming to the performance, again you can observe the processor cache. That is you have a main memory, and you have in the processor associated with that is a cache memory, and it is interconnected through a bus. The processor time to execute the program, majorly it depends upon the hardware which is involved in executing executing individual machine instructions. So the performance, the processor and a relatively small cache memory, it can be fabricated into a single integrated circuit chip. Main purpose of that is it increases the speed, means no need to fetch the instructions from the memory, as it is available within the processor itself. The speed of that can be increased, but cost of that will be increased. Suppose if I want to have a memory inbuilt, the cost of the system will increase, and you need to have a memory management unit, MMU. So first one, if you observe the clock, processor clock, so you will have all the operations whatever you perform, all the processor circuits which are controlled by a timing signal which we call it as a clock. So the clock usually defines at regular intervals of time. We call it as a clock cycles, at regular intervals of time, clock cycles. To execute a machine instruction, the processor divides the action to be performed into sequence of basic steps. So such that each step can be completed in one cycle, one clock cycle. Suppose if I consider the length of the clock cycle as P, it is an important parameter which affects the performance. The inverse of that, which will give you the clock rate, the rate at which it is performing. So clock cycle is represented as P, whereas the rate at which it is performing is 1 by P, which we also call it as, which is measured in terms of cycles per second, or we also call it as clock rate, hertz, frequency in hertz. So the execution of each instruction here, it is divided into several steps, that is basic steps, each of which will be completed in one clock cycle. So you have a megahertz, gigahertz, or billion of instructions, which will be 500 million instructions, 500 megahertz, 500 million cycles per second, meaning is that. So usually we call it as a 500 megahertz. So coming to the basic performance equation. So where T here, the T indicating, after knowing that the processor time component of the total time elapsed. So let us consider T is the processor time required to execute a program, one program that has been prepared in high level language. So from high level language it has to be converted into machine language, then it has to be executed. So total overall time, if I consider as capital T, then N, capital N indicating number of actual machine language instructions needed to complete the execution. So that means, suppose if you have a loop, machine instructions, first high level language is converted into a machine level language. So N, if it is indicated as a number of actual machine language instructions needed to complete the execution, then S, capital S, indicating average number of basic steps needed to execute one instruction in that. Suppose if I have in a program 10 instructions, so each instruction is requiring a time as S, and total instructions in that is N. N into S obviously gives you the total length or total time taken by the system to complete the machine instructions, to complete the execution of a program. Then suppose if I say R is the clock rate, means the rate at which it is performing. Clock rate, this is a frequency, inversely proportional. So how do we calculate the total time required to execute the machine instruction? Means capital N into capital S, which will give you the total length of time needed to complete machine language instruction or program which is written in machine language. At what rate it is performing each and everything is measured in terms of R, 1 by R, which will give you the time, because T equals to 1 by F. 1 by R means divided by R, which will give you the total time required to complete the execution of a program. So we call it as this as a basic performance equation, T equals to N into S divided by R. Now what we need to do is, you need to improve the performance parameter T value, we need to improve it. If I want to improve that to achieve a higher performance, the two ways that you can do, that is, I need to increase reducing the value of performance, means execution time, I need to decrease it. If I want to decrease it, obviously N value, S value, if I reduce, then T value, as it is directly proportional, you can reduce the time required to execute the program. And you can see R is inversely proportional. If clock rate is increased, frequency of the system is increased, obviously execution time will also get reduced. So N and S has to be decreased, and you need to increase the value of R. Suppose if the value of N is reduced, the source program is compiled into fewer machine instructions. If I want to reduce the value of S, indicating a smaller number of basic steps which you need to perform, or if the execution of instruction is overlapped. Then higher clock frequency, if I make use, R value will increase. Obviously the time required can be reduced. So this is a effect of a basic performance equation of a system. Coming to the next one, which is a pipelining and a superscalar operation. Name itself indicates pipelining. Instructions here are not necessarily executed one after the other. We can't wait till the completion of first instruction to process the next instruction. Instead, what we can do is, as we know that each instruction will be segregated into, each instruction will be divided into small sequence of basic steps, small instructions. So whenever you perform some basic step in that first one, next instruction can be fetched into. So the value of S, which does not require to be the number of clock cycles to execute one instruction. Whereas pipelining, it is indicating a overlapping of the execution of successive instructions. Suppose if I want to add R1, R2, R3 at the same time, processor reads the next instruction in the memory. So here you can observe non-pipelined one and pipeline instruction. You will be fetching the instruction first and started executing. You need not to wait for the next instruction to fetch till the completion of execution of first instruction. So you'll fetch the second instruction. By that time you execute the second instruction, fetch the third instruction. And next one, again you fetch the third instruction. After completing the execution of third one, fetch the fourth instruction, and so on it goes. Whereas in the non-pipelined case, you wait till the completion of first instruction in order to execute the next instruction. So what it will do is, as you are performing a multiple instructions, pipelines which are implemented together, processor time reduces. Actually, performance of the system will improve. The main goal here is we need to reduce the value of S. S value, how can I reduce? Means using a pipelining technique I can reduce the value of S. So coming to the next one, which is a clock rate, R value denoted as R. Clock rate I need to increase. So increased clock rate I need to increase the performance. So improved integrated circuits that you can, integrated circuit technology you can make use to have a faster circuit and reduce the amount of processing done in one basic step. If you reduce even that, in that case clock rate can be increased. Increasing in the value of R that are entirely caused by the improvement in IC technology, which affects all the aspects of processor operation equally except the time to access the main memory. Coming to the next one, which is a performance measurement. T is the one which is a difficult parameter to compute. You need to measure the computer performance using a benchmark programs. Overall computer, how it is performing, you can perform that by using a performance checkup that can be done by using a benchmark programs. Spec is the one group corporation, System Performance Evaluation Corporation. They select and publish representative application programs for different application domains together with the test results for many commercially available computers. So which you need to compile and run, no simulation part. So you can take that with respect to the reference computer. So spec rating, N means spec rating which you can calculate. So running time on a reference computer with respect to running time on a computer which is under test. So spec rating for n values means n programs in a suit if you perform, which is a product of all the values, a product of all the time required for spec rating of each and every program. You can calculate and you can specify the performance measurement of this. This is about the first part of their first module in case of CO, computer organization. Thank you. In the coming sessions we will study about performance measure, means we'll study about the memory allocation, addresses, operation, assembly language, all these things which we will study in the next sessions. Thank you.